All right. So this lecture is about the existence and uniqueness theorem for initial value problems. What's an initial value problem? So let's talk about what it means to be an nth order initial value problem, which I'll abbreviate as IVP. This is a differential equation which in standard form will be yn, nth derivative of y, is some function of x, y, y prime, till the n minus first derivative of y. That's the differential equation, and that's nth order. But because it's an initial value problem, that also means that we specify at one initial point x0, the value y of x0 is y0, the derivative, the value of y prime of x0, which we will call not y1, but y prime 0. This is just a number, until the n minus first derivative at x0 is some initial value, which I'll call yn minus 1, 0. Okay? So there are n initial conditions because the value of y is, if you like, the 0th order derivative until the n minus first order derivative. And just so you see that this has physical meaning, we will, I'll give you one physical example. I have a spring, and this is in a place without any gravity, so never mind the fact that it looks as though it's going down. And we want to discuss the motion of the spring. And so what you have is that the only force on it is a function of y, which is the extension of the spring. And so this time, instead of making the independent variable x, I will make it t to emphasize this is time. And the force is minus ky, which is also my double prime, right? Mass times acceleration is the force, and minus ky by Hooke's law is also the force, because that's proportional to the extension, k being Hooke's constant. So the differential equation, after you solve for y double prime, it's y double prime equals minus k over my. For example, y double prime equals minus 4y if you want. And then the initial value problem, this is a second order differential equation. You would write y double prime equals minus 4y, and you didn't say the initial time, y of 0, for instance, is y0. This is what you might call the initial position. For instance, the initial value is 3, and then y prime of 0 is, I called it y prime sub 0, but let's call it v0, which is the initial velocity. For instance, y prime of 0 equals 7. So that would mean that you pull this 3 units down and then give it an initial speed of 7 units down, and then you watch it oscillate. And the initial position and initial velocity, notice it's the derivatives up till, but not including the derivative of the differential equation, and that tells you what state the equation starts in, and then you can expect it will continue. Okay? So basically the principle is, if I have a nice initial value problem, then there should be that the initial value problem would, pretty much uniquely determines the solution of y of x. So here I wrote it in terms of t, but it doesn't matter what you call the variables. Okay, so before I state the general solution, let me just show a general theorem. Let me tell you a bit of the things that go wrong if you don't have a nice differential equation. Okay? So let's do a few examples. First example, let's say I have a differential equation of the form x y prime plus y equals 0 and y of 0 equals 1. Okay? So notice, this is not in the standard form. To put it in standard form, you would need you would need to write it as y prime equals minus y over x. Good? Okay, and so this is the function of x and y. And by the way, I'm going to mostly do this in the case of a first order IVP, so it's y prime equals f of xy, and you just have one initial condition, y of x0 equals y0. Good? So this is the example where we will state the theorem. We won't prove it. But something similar works for any order differential equation. Okay, so you have something like this, and y of 0 equals 1. And notice this has no solution because we have at x equals 0, the differential equation says 0 times y prime at the moment 0 plus y of 0 equals 0. So 0, whatever the derivative is at 0, multiplied by 0 gives me 0, and then plus y of 0, but that's 1 equals 0. This is a contradiction. Okay? So this tells you you actually do not have any possibility of having y of 0 equals 1. That contradicts this equation. Okay? No solutions. Okay, so I'm going to make a small digression for something we will see later. I wrote this differential equation in a way that it's very easy to solve, even if you don't know differential equations. Note, if you look at xy prime plus y, xy prime plus y is the derivative of x times y, because xy prime is x prime y, which is 1 times y, plus x times y prime, and that's equal to 0. So if x times y is something whose derivative is 0, that means x times y is a constant. And so notice, so usually y equals c over x is a solution. And notice these things can't really pass through y of 0 equals 1. On the other hand, if I chose a different initial value, say y of 1 equals 1, I could get y equals 1 over x. Or y of 1 equals 7, then I would get y equals 7 over x solving for c. Okay? So whether your differential equation, your initial value problem has a solution depends on where the initial value is. Also note that there's another solution which is just y equals 0 constant. That's not exactly covered by this because this is dividing by, that would be dividing by 0 when x equals 0, but y of 0 equals 0 is a perfectly good, sorry, y of 0 equals 0 is a perfectly good initial condition with solution y equals constant function 0. Okay, so just so you know, all theorems we're going to state will be, if you like, sufficient conditions, but not necessary conditions, and you shouldn't read into theorems more than what they say. Okay, that's the first example. Now let's do the second example. This one is y prime equals 3y to the 2 over 3. All right, so this differential equation, it's not yet an IVP, so let's say y of 0 equals 0. Once again, this turns out to be a slightly funny initial condition, and you'll see. So here, some solutions immediately pop out to mind. For instance, y equals 0, constant. That certainly has its initial value as 0. And this also has that the derivative is always 0, and 0 is 3 times a positive power of 0, no problem. Okay? But there's another solution that I'll explain where it comes from later. But there's y equals x cubed is a solution because y prime is 3x squared, which is 3 times x cubed to the 2 over 3, which is 3 times y to the 2/3. So x cubed satisfies the differential equation, and of course it satisfies that when x is 0, y is 0. By the way, in these examples, I'm mostly taking the initial value x sub 0 to be the number 0. It does not have to be this way. This is just for simplicity in the lecture. In real life, you don't always get this. But if you're modeling, you try to maybe if it's a differential equation in terms of time, you might try to count time from your initial condition. So it depends, but the theorems work for any x0 and any y0 if you have the right hypotheses. Okay, so notice a solution exists, but is not unique. Is that good? Now notice there are more exotic solutions, and I want you to understand that what can go wrong is more subtle than just, oh, I found two solutions. So I want to take a moment and say something about this. First of all, note, if y is not equal to 0, then y prime over 3, or let's say over y to the 2/3 equals 3, right? Now that's not permissible near the initial condition. But just let's think about this differential equation. So this looks like y to the minus 2/3 y prime equals 3. Now this almost could be something which is the derivative of something, okay? So here the point is that what's the derivative of y to the 1/3 prime? Well, this is 1/3 y to the 1/3 minus 1, which is minus 2/3, times y prime, because this is derivative with respect to x, and you must always remember the chain rule. Okay? So what is this telling me? So this is telling me that, let's see, dividing by 3 on both sides, this left-hand side is y to the 1/3 prime equals 1. So what function has 1 as a derivative? It has to be x plus c, and y equals x plus c to the 3 is a solution. I'm not saying it is, certainly it will not satisfy this unless c is 0. But I just mentioned that there are these families of solutions. And what I want to do is I want to sort of draw for you what this looks like. Okay? So here, like we did in a previous lecture, we can draw a direction field. When y is 0, y to the 2/3 is 0, and that means slope 0. When y is a little bit positive, y to the 3/3 is a little bit positive. And it's sort of, actually it's, can look like this. When it's negative, maybe I should mention, when y is negative, you should think of it as 3 times cube root of y squared. So cube root of y always makes sense, and this is positive. So you get a slight positive slope here. And what happens is that if you start from this initial condition of 0, 0, and then if you go forward in time, you can stay on this, but you can also go up like y cubed. If you go back, x cubed. If you go backwards in time, you can stay horizontal or you can go down. And now here's the worst part. If you take a function like x plus c to the 3, that's a shifted version of y equals x cubed. And there's infinitely many shifted versions. And what you can have is that you have a solution. For instance, y equals 0 if x is less than or equal to 0, and x cubed if x is greater than or equal to 0. That I will draw in green, perhaps. And it goes, 0 for negative time, and then like x cubed for positive time. And the situation is even worse than you think, because, for instance, you could have a solution which is negative on this bit, stays horizontal for a while, and then goes up again. I'm not going to write a formula for this, but you know, for y less than something, it's of the form x plus c cubed for some constant. Maybe this is x plus 8 cubed, okay, which at x equals minus 8 goes to 0, then it goes horizontal, and then until here, maybe it's x minus 10 cubed after that. So you can cut and paste together solutions. And these are all differentiable I want to emphasize that because, okay, this function is continuous. You glued together the value at 0, but also x cubed has a horizontal tangent line at 0, and as does the constant y equals 0 have a horizontal tangent line. So putting them together, you're genuinely something which is differentiable at 0. There's no tricks involved mathematically. This is a genuine solution to the differential equation. So I hope this shows you that there are some strange phenomena that can happen. Now, of course, I should also show you the nicest situation when you actually do get a solution which is unique in some suitable sense. Okay, let's put that here. I just want to keep the statement of example 1, because once I state the theorem, I will have more to say about it. Okay, so example 3, let's take y prime equals y and y of 0 equals 1. Okay. This has an obvious solution, which I chose so that you could, if you're familiar with functions, what function is its own derivative? The exponential function. Okay, and the exponential function, more or less, I chose the initial value which corresponds to e to the 0 equals 1. So y equals e to the x not only is its own derivative, but its value at 0 is 1. Okay? And we claim this is unique. Okay? Okay, now here's the fake argument. Because the real argument is from the theorem. But the fake argument goes as this. So the solution exists. I showed you a solution, so there's no problem. The question is there any other solution? You know, could there be something we didn't think of? Maybe we saw y equals 0 in this case, but we didn't see y equals x cubed, or we saw these two, but we didn't see some of the other possibilities. How do we know this is the only possibility to this IVP? So the fake argument, but it's nearly complete, is any solution is differentiable, hence continuous. Okay, this is a bit of culture for you. You don't have to take it too seriously, but I want to mention it. So if y prime exists, then y is continuous. And so if y of 0 equals 1, which is a positive number, that means you're passing through an initial condition like this. So any continuous function can't suddenly jump below 0. At least for x close to the initial values, then y of x is positive for x close to 0. Good? Okay, and then we have y prime over y equals 1, and this is permissible because y is not 0. This is at least permissible for x close to 0. And then this is the derivative of log y. Normally we'd have the absolute value, but this is why I mentioned that y is positive and I'm not writing the absolute value. So log y prime is y prime over y equals 1. And what function has derivative 1? Exactly log y equals x plus a constant. And basically you get that the solutions, oh, I didn't mean to erase that. Let me keep it up there as example 2. Y prime equals 3y to the 2/3 y of 0 equals 0. And now I have access to the whole board. Okay. So, for example, so y equals e to the x plus c, which is of the form a e to the x. Actually, if you allow a to be negative, you would get other solutions, and that is the general solution. We'll see why later in the course, a more careful general proof without using the theorem. But for today, here we have the initial condition when x equals 0, y equals 1. So a 1 equals y at x equals 0, which is a e to the 0, or let's write it as a to the e to the x at x equals 0, which is a, and therefore a equals 1, and therefore y equals e to the x. So notice this is a sort of plausibility argument for why this is the only solution. Okay? Now you don't want to do this for every single differential equation you find. You want to have general theorems which tell you when a differential equation has a solution even before you start working. And that's the content of the main theorem of today's lecture. It goes as follows. There are two theorems. There's first the Peano existence and uniqueness theorem. Given the IVP, y prime equals f of xy, and y of x0 equals y0. This time I will draw x0 and y0 as being non-zero numbers. Assume that the function f of xy is continuous on a rectangle, possibly small, R, containing the point x0, y0. So think of f of xy as a function in the plane. This is the domain. And the rectangle looks like this. And the initial condition is over here. Okay? Then a solution to the IVP exists for x close to x0, i.e. for x in some interval where x is between x0 minus h and x0 plus h. Okay? So I have a differential equation which gives me some kind of slope field, you know, whatever it is, and it is possible to actually follow the slope field at least potentially in some small region, okay? Not necessarily all the way to the end of the rectangle, okay? So this would be x0 minus h, and this is x0 plus h, and the solution is somewhere here, okay? And we're not going to try to prove this, but let's sort of see why it is true in our cases. This is just existence. So notice this is exists, and it's not necessarily unique. And I emphasize this is a sufficient condition for existence. You have cases when an IVP can have a solution even when this f is not continuous, although it would be, I don't want to give an example of that really. You can, actually the case when y of 0 equals 0 here is one of those examples. Anyhow, if you have that this function is, f is continuous, then there is at least one solution, but possibly more than one. So let's take a look. What went wrong here when there were no solutions? Well, f of xy is minus y over x. That's okay, except when x is 0. So f of xy good for case 1 is when x is not 0. So either in this half plane or this half plane, and the origin, so this is good except on the y-axis, and the initial condition is at y of 0 equals 1, sorry, not y of 0 equals 0, that's a bad point. The theorem does not guarantee anything at bad points. You're not guaranteed there's a solution. But if I took an initial condition somewhere out here, I could get one of the solutions which we talked about of the form y equals constant over x, okay? And notice at y of 0 equals 0, there is a solution, even though that's a bad point. So don't read into theorems more than they say. The theorem just says, if you have a nice continuous function, then that's sufficient to guarantee a solution. It is not necessary. Okay. So that's the first theorem, the Peano existence and uniqueness theorem. And then the second theorem is the Picard, or most people call it Picard-Lindelof existence and uniqueness theorem. Oh, goodness. I see that I wrote something stupid here. Okay, all of you have been watching. I hope you noticed. This and uniqueness is totally not true. This is just an existence theorem. But in the enthusiasm of the moment, thinking ahead, I mentioned the wrong word. This is only an existence theorem. This is not an theorem about uniqueness, the first piano theorem. I apologize for that. However, the second one, I guarantee, is an existence and uniqueness theorem, so that is better. Oh, goodness. Okay, please make sure that you correct this in your notes. Okay, now let's talk about the Picard-Lindelof existence and uniqueness theorem. So here, if furthermore, the IVP above has both f of x, y, and the partial derivative of f with respect to y continuous on the rectangle R, on a rectangle R, containing the initial condition, then having both the function and its partial derivative with respect to y, you don't need x, funnily enough. If both of those are continuous, then not only does a solution y of x to the IVP exist, but it is also unique on a small interval, so x0 minus h less than x0 plus h. Okay, so notice the piano case, when you only had continuity, that was sufficient to be sure that some solution existed. I repeat, it is not necessary, but it is sufficient. Similarly, if you have continuity of f and of its partial derivative, that's a stronger condition, and that is sufficient to guarantee that, in fact, the solution exists and is unique, and that's kind of amazing. Okay, so let's see what's happening with these. So 1, the function wasn't continuous at all. Okay? Now 2 and 3, they cover both of these cases in interesting ways. Let's look at them. Problem in case 2, the function y, so this is now f of xy. So for 2, f of xy, which is 3 times, well, if you like, cube root of y squared, this is a perfectly nice function. It's continuous. So no surprise that solutions exist. It's continuous on all of r squared. But the partial of f with respect to y is 3 times, better do it from the y to the 2/3, times 2 over 3 y to the minus 1/3, which is 2 over cube root of y. And this is not continuous when y equals 0. Okay? So I'll come back to the other example after this. Here you get, for 2, you have to cut out the bad initial points for Picard-Lindelof, but they are good initial points for piano. Okay? So what it's saying is that here, I started with y of 0 equals 0. A solution existed by Peano's theorem, but it was not unique. And the fact that it's not unique is not surprising because, okay, this condition, as I said many times, is sufficient but not necessary. But if the condition doesn't hold, it is very possible to get more than one solution. And this is an example of that. So where you can either go like this, or you can go like this, or you can go like this, or you can go like this, horizontal this, all sorts of solutions passing through this initial point, because that's a point where the hypotheses are not satisfied, and so you cannot deduce uniqueness from the theorem. The theorem tells you the solution might not be unique. You're not sure. You have to think more about it in those situations. Okay. On the other hand, for 3, we have y prime equals y, which is f of xy, and df dy, it's 1. These are continuous everywhere, so all initial conditions are good for Picard-Lindelof, and you always get a unique solution. Is that good? And in fact, I erased it a while ago, but the most general solution to this is always y equals ae to the x, and given any x0 and y0, you can always solve for a. And we will see a lot more of this as the semester goes on. Okay, so I want to say one last thing about this. I only said the solution has to be close to x0, so I want to say something quick about that. Okay, so in that case, let me just keep this statement of Picard-Lindelof, and let me erase the piano. It's piano, not piano, by the way, an Italian mathematician. And I'll even erase the first order initial value problem. Okay, so remark. First of all, if I have y prime equals f of xy, and it's nice for Picard-Lindelof, this is something we talked about in the previous lecture. So if I have an x0 and y0, there's only one solution here. You cannot have two solution curves intersecting. Because if I have something like this, this contradicts the uniqueness part of Picard-Lindelof. So when we were previously drawing solution curves by looking at the qualitative behavior, they were first order equations, so the initial condition was just the initial x0 and the initial y0. And if two solutions have the same, pass through the same point, they would have the same first order initial condition, and then they would have to be the same, assuming a nice differential equation. So that's why in the examples we did in class before, those solution curves never intersected. Okay, and second, the thing I've been promising you about, having to do with the fact that you only have a solution in a small interval. It can be told how small in a more advanced version of the theorem that you're guaranteed at least you can go this far forward and this far backward in x, but we won't do that. We'll just say some small interval in this course. Okay, so let's do the example of y prime equals minus y squared. Okay? So this is again f of xy, and y of x0 equals y0. And here, f equals minus y squared, and df dy is minus 2y, and both are continuous for xy in R2, for all xy in R2. So all initial conditions are good. Okay? So no matter what initial condition I give, there is a unique solution close to my x0. However, this is a little bit trickier than it seems. So let us mention that note by integrating minus y prime over y squared equals 1. So this is 1 over y quantity prime equals 1. And integrate both sides, so 1 over y. Its derivative is 1, so this is x plus c. So we get a family of solutions y of x equals 1 over x plus c. We also have a solution y equals 0 constant, right? Because that pretty clearly gives me that when y is 0 constant, and when y prime is minus y squared, which is 0 constant, that's compatible. Okay, so notice something interesting happens here. We have uniqueness of solutions near the initial points, but it is trickier to say this precisely than you might think if you just calculate it blindly. You have to think, what does this mean? Okay? So for instance, for example, if I put y of 0 equals 1, right? That means you pass through this point. Okay? And a solution satisfying this is y equals 1 over x plus 1. Okay, certainly when c is 1 over x plus 1 at x equals 1 just gives me 1. And so this is unique for x in an interval containing x0 equals 1. So right here, x0 is 0 and y0 is 1. And of course, x0 should be equal to 0. Correction. Okay? But then when we think, what does this solution look like? 1 over x plus 1 has a problem when x equals minus 1. So the solution, if you follow the slope field, which y prime equals minus y squared, so here the slope is minus 1, here the slope is 0, etc. Here the slope is also minus 1, by the way. Okay, and here it's further. So if you follow the slope field, it takes you like so, and it takes you like so. But notice the slope field does not tell you what happens before x equals minus 1. The solution blows up as x approaches minus 1 from above. So the largest such interval for this solution is x between minus 1 and plus infinity. So there's a problem of blowing up as you approach minus 1. Okay? So notice this particular example is infinitely long on the right, but I'll give you right now an example where that doesn't work. Okay? But if I took another initial condition, so if the initial condition was at 0, I would get a solution 0 everywhere. If I put an initial condition y of 1 equals 7, then I would get something like 1 over x minus 6 over 7. And you know, it just gives you bits of hyperbolas which always have a place with a vertical asymptote. And the solutions you want only go as far as the function is sort of connected to your initial condition. The bit of 1 over x plus 1, which is down here, this is not part of the solution to the IVP. You can't reach it just by following x and following the slope field. So be careful. Okay, one last remark. Something for you to think about. Y prime equals y squared plus 1. Okay? And show that the general solution is y equals tangent of x plus c. Hint, divide by y squared plus 1, always permissible. And the derivative of arctangent is 1 over, so you have y prime over y squared plus 1 is the derivative of arctangent y. Always remember your chain rule. You need 1 over y squared plus 1 times y prime. So this is saying arctangent y prime is 1, so arctangent y is x plus c. So this gives you something like that. Okay, and then, so y if y of 0 equals 1, the solution is, the unique solution is y equals tangent of x plus pi over 4. This I'm leaving for you as an exercise to work out. Okay? And this is valid where? So the solutions, tangent x plus c, so tangent x looks like this. And if you have tangent of x plus c, they kind of look like that. So tangent x sort of goes off to infinity at minus pi over 2 and pi over 2. And for instance, tangent x plus pi over 4, which is, this is valid for x between, or let's say x plus pi over 4, between minus pi over 2 and pi over 2. So x between minus 3 pi over 4 and pi over 4. So when you work out this explicit one we want, it goes to minus pi over 4 and pi over 4. And then when you follow this slope field, starting from the initial condition 0, 1, at some point the solution blows up in positive direction and in the negative direction. Okay? And if I'd done something like y prime equals 1,000 times y squared plus 1, it would blow up sooner, and then this interval could be much closer to 0. So you don't know, based on what we have talked about in this course, how far the solution exists. That is beyond the scope of Math 202, but you should know such results are known if you need to look them up in a later semester. Okay, that's it for this topic. Thanks.